Hello students, today we are going to see some more interesting and important questions from Narendra Avasthi sir's Physical Chemistry Redox Reaction Level 2. Come on, let us discuss few more questions from this session. Here, the first question. To a 10 ml, 1 m aqueous solution of Br2, excess of NaOH is added so that all Br2 ion, that is all Br2 is disproportionated to Br minus bromide and bromate BrO3 minus. The resulting solution is free from Br minus by extraction and excess of OH minus neutralized by acidifying the solution. So the reaction, it has taken two reaction, that means basic medium as well as acidic medium, right? So acidifying the solution, the resulting solution is sufficient to react with 2 gram of impure calcium oxalate. Molar mass, it is 128 gram per mole sample. The percentage purity of oxalate sample, this sample we have to identify. Right now, first and foremost, here two things we have to note down. First point, disproportionation reaction, and second thing, it is acidic. What it is, acidic medium as well as basic medium, both it is reacting. And finally, we have to identify through this, we have to identify the percentage purity of oxalate sample, right? Come on. Let us go and identify first and foremost disproportionation reaction. What do you mean by disproportionation reaction? You know very well. Right now here in this point, disproportionation reaction as a single atom or ion or a molecule simultaneously oxidized and reduced. So that is called disproportionation reaction. That is that playing in a two role. That means double role it is playing, which what it is actually atom or ion or a molecule, a specific atom or ion, a molecule plays a role of oxidation as well as reduction. That means oxidized as well as reduced in the same atom or ion or a molecule. I hope you got that idea. So it is oxidized and reduced, that is with one higher oxidation state and another with lower oxidation, that means lower reduction, reduced state. Okay, now in this question they mentioned about bromine combined with the basic sodium hydroxide, you will get this one, that is Na plus Br minus, and the same way Na plus BrO3 minus, right? I hope you got that idea. Again, this BrO3 minus again combined with calcium oxalate, that is what it is, 2 gram of calcium oxalate, that is yes, 2 gram of calcium oxalate, that is ion I just mentioned. In the acidifying solution, in the question it has mentioned acidifying solution. So you are getting this bromide ion, carbon dioxide and water. Yes. So that means here what it is, one with the lower oxidation, that means one with the higher oxidation state and lower reduction state. So I just to bring that equation for you to understand. The same way Br2 and OH. So here you will get what it is, this Br2 0, that is oxidation state, it is 0. When returns to that product side, it is actually Br minus. So it is -1 oxidation state. So that means 0 to -1. And the same way BrO3 minus. See now here the oxidation state 0 to, here actually what it is, +5 oxidation state. I just to bring that idea for you how to analyze that oxidation state, how to find out that oxidation state. X and oxygen for how many atom of oxygen, 3 into -2 equal to -1. So you will get what it is, +5 oxidation. So 0 to +5. So oxidation, higher oxidation and lower reduced state. So this is the way I would like to explain all these ideas for you to understand this question, right? I hope you got that idea about disproportionation reaction, how it is possible two reaction in one point. That means here bromide ion and bromate ion, that is with acidic medium as well as basic medium, it has taken place. Now we have to analyze the data and finding the answer for this question. I hope you got this point. Right now here in this moles of bromine, initially how much it is. Okay, so actually this reaction, it is divided into two reactions. That is, one is acidic medium, the other one it is basic medium. So first one it is basic, the other one it is acidic medium. That is what I just brought this to equation, right? I hope you got the clarity. This is basic medium, this is acidic medium, right? Because it is acetate ion, no, so this is acidic medium, right? Okay, now here moles of Br2. So initially moles of Br2, what it is here, molarity into volume. Moles of Br2, generally moles we are finding means molarity into volume, right? So molarity into volume, they mention what it is, molarity 1 m, and volume it is actually 10 ml they mentioned, right? So that means what it is, mole you will get ml only, no. So you will get millimole only, right? You will get what it is? Millimole. So 10 millimole. I hope you got that idea. Yes. Now moles of NaBrO3, right? This is Br2. Now here moles of NaBrO3. So this is actually balanced equation. What I mentioned here in this point, here you see 3 moles of bromine can provide here what it is BrO3 minus. In this equation also 3 moles of bromine can provide here NaBrO3, right? That means here bromine, it is a 10 mole. So that means NaBrO3, that is equal to, actually how do we identify? That is equal to, this is equal to here 10 by 3, right? Now this is millimole only. So the same millimoles of NaBrO3, that is equal to 10 by 3. Right now, actually we go and identify for that moles of calcium oxalate, how much it is required. So calcium oxalate, according to that equation, balanced equation, BrO3 minus plus 3 moles of calcium oxalate, that is oxalate ion I just mentioned, C2O4 2 minus. So 3 moles it is required. So here 3 moles are there, but how much moles it is required? So therefore calcium oxalate, millimoles of calcium oxalate, CaC2O4. So here you see millimoles of millimoles. This is also millimoles only, because everything we did not mention it is a mole, because it is 10 ml. We just bring it as it is. We did not convert it into liter. This is ml only. Now you see volume in ml only. So that means millimole only. So this is moles of bromine, and this is millimoles of sodium bromate, right? And therefore millimoles of calcium oxalate. Actually, how much it is there in the balanced equation? 3. So across multiplication, for millimoles of sodium bromate, it is 10 by 3 means, therefore millimoles of calcium oxalate 10 by 3 into 3. So you will get how much? 10 millimole, right? So 10 millimole. Now here this is also 10 millimole. This is also what it is, calcium oxalate also, it is actually what it is, 10 millimole, right? Now that means required, this we can mention, it is actually required moles of calcium oxalate, required millimoles of calcium oxalate, C2O4, right? I hope you got that idea. So this is the answer. Now we have to identify the mass of that, actually what it is. Mass they have provided in the question, only 2 grams they have provided, and what it is, given mass only they have provided, that is 2 gram, and mass percentage we have to identify. So this is millimole, we just converted into mole. So that means directly we can go mass of CaC2O4, that is actually 10 into millimole, right? 10 to the power of minus 3, we just converted into mole. Millimole we converted into mole. This is actually mole, millimole into actually molar mass. Now you see mass of calcium oxalate. This is molar mass. Just now in the question only they mentioned 128 gram per mole, right? Now here divided by what it is, sample mass into 100. This is percentage of mass of calcium oxalate, right? So here millimoles into molar mass of calcium oxalate divided by sample mass. See, everything I just mentioned very clearly for you to understand. I just explained at this point also for you to remember. Simply you can't apply the values unless you should know the concept. The sample mass, how much is sample mass here? Actually 2 gram. Here 2 gram. Okay, now what is the answer you'll be getting? That means here 10 into 10 to the power of minus 3. So you will get 10 to the power of minus 2 into 128 gram per mole divided by 2 gram into 100. I hope you got that idea. So this gram and gram will be cancelled. Right now, here when you calculate this, you will get what it is. 264. So 64 percentage. 64 percentage, 10 to the power of minus 2, and here multiplied with what it is, 100. So you will get 64 percentage. See now how clearly you got that idea, but it is little bit lengthier sum, but you should understand very clearly. That is the reason I have explained in a long way process. Now, which is the correct option? Option D is the correct option, 64%. Right, I hope you got that clarity about this question. What is that disproportionation reaction? How to deal this question, that is equations according to that, how many moles it is there, how many moles required. From that, how do we identify the percentage mass, that is the percentage purity? Yes, I hope you got that idea. Now, if you want, I will give another idea, that means another method. Right now, here the same thing only. See here, 3Br2 plus 6OH. You're getting what it is? Br 5Br minus BrO3 minus 3H2O, and this is first equation, second equation as it is I mentioned. And the same way here, 10 millimole. How do you get 10 millimole? That is what I just explained for you. So 10 millimole can produce 10 by 3 millimole of BrO3 minus. That, as I mentioned, here they have given. Right now here calcium oxalate required 10 by 3 into, so here 10 millimole. So the same thing what I mentioned is the same thing only here, percentage purity they have mentioned. Hope you got that clear idea. According to this point also. Yes, come on, let us go to the next question. So 64% as the answer for this. 0.10 gram of a sample containing copper carbonate and some inert impurity was dissolved in dilute sulfuric acid and volume made up to 50 ml. Right, the solution was added in 50 ml of 0.04 m potassium iodide, where copper precipitate as copper iodide and I minus is oxidized into I3 minus. A 10 ml of portion of this solution is taken for analysis, filtered and made up free I3 minus, and then treated with the excess of permanganate ion to liberate iodine. Required 20 ml of 2.5 required 20 ml of 2.5 millimole of sodium thiosulfate to reach the endpoint. Now in this, here determine the mass percentage. So here also in this question also, finally what we are going to identify, mass percentage of the sample of calcium, copper carbonate, right? But here two equations are, that means two reactions are available, right? I just bring that idea for you to understand in the picture way. I just taken. Right now in that beaker, here 50 ml of dilute sulfuric acid has taken and 0.10 gram of copper carbonate, which is dissolved inert. Okay, this is the sample, 0.1 gram of copper carbonate, which is dissolved in 50 ml of H2SO4. Right now in that, what we are going to add, we are going to add 50 ml of 0.04 m, that is molarity of potassium iodide. Right now here potassium iodide we added now. Now for that, copper precipitate, the solution where copper precipitate has taken here, copper precipitate as CuI and I3 minus is oxidized in that 10 ml portion. So the reaction takes place. So here copper carbonate plus iodine combined, this potassium iodide combined, you are getting copper iodide I3 minus, it is produced. Now in this portion 10 ml has taken. Why do we take that? To treat with that acidic permanganate ion to liberate I3 minus. So to completely eradicate it I3 minus, we are adding what it is, it is treated with this. In that 10 ml we have taken for that to eradicate I3 minus. For that, what we are going to do, for this required 20 ml of 2.5 millimole of sodium thiosulfate to reach the end point. Now you see all these, this point is one and this is another point and the last one, this is another point. I hope you got that idea about how to, what are the points are here and how to analyze that question. Now finally, we have to find that, identify the mass percentage of copper carbonate, right? See, this is like going around the neck only, but yes, come on, let us check. So first and foremost, iodine I minus plus Na2 S2O3. It gives actually what it is, what it can provide, Na2S4O6 plus NaI, potassium iodide we are getting, right? Okay, now this is I2 minus. Okay, that is what I minus, I just mentioned I2 minus. Right now here in this point, we have to find out the moles, that is actually millimoles only here. So what are the points? What it is, millimoles of potassium iodide. Here how much we have taken potassium iodide, here very clearly I just mentioned 50 ml of 0.04 m potassium iodide we have taken, right? What it is, 50 ml of so millimoles equal to what it is, moles, how to identify potassium iodide, moles, how to identify molarity into volume of the solution. Molarity, it is 0.04 m. Volume of the solution, it is 10 ml, right? Right, 10 ml. Yes, sorry, let me go through for you. Yeah, it is 50 ml, sorry, 10 ml, because it is 50 ml. See, datas are very important, sorry for it. So here 50 ml. Now, this is ml only, so you will get millimoles only. So in this question, basically everything it is based on millimoles. So what is the answer you will be getting? You will be getting 2 millimole, right? You got 2 millimole of potassium iodide. 1 point we got it. Another point, milli-equivalent we have to identify. So milli-equivalent, it is milli-equivalent of sodium thiosulfate. Milli-equivalent of sodium thiosulfate, Na2S2O3. React with 10 ml of 10 ml of iodine, I minus. This is the point I just remember. I just mentioned last point. It is 10 ml. So here I minus 10 ml. From this here 10 ml we have taken also. Now you see 10 ml has taken for the analysis to treat with acidic permanganate to liberate what it is, I3 minus. So here only we have taken 10 ml of iodine, right? So here what are the points to be noted down here? Here what are the points to liberate iodine? 20 ml of 2.5 millimole of sodium thiosulfate. So here 20 ml into 2.5 millimole. So 10 to the power of minus 3 in, and that is millimole we have taken. No, so it is how much we will get here? You will get 50 into 10 to the power of minus 3, right? So milli equivalent of sodium thiosulfate, which is reacted with 10 ml of iodine, right? Now here milli equivalent of unreacted point we have to identify. So unreacted point means here how much solution it is there in the beaker. In this 50 ml of dilute sulfuric acid, in this 50 ml of potassium iodide solution. So these both are available. First one we have taken 0.1 gram of copper carbonate, which is dissolved with dilute sulfuric acid. So that is one amount, that is 50 ml. Add 50 ml of 0.4 m potassium iodide solution to what? To liberate this point, right? So here potassium iodide we are adding, no, copper iodide become as a precipitate, iodine I3 minus also it is coming, that is liberated with what it is, permanganate ion, right? Okay, now how much altogether? 50 plus 50, 100. So here in the 10 ml only we have taken for the analysis, so that means unreacted point is also available, right? So milli equivalent of, I just write that, milli equivalent of I minus, that is iodide ion, left unreacted in 100 ml of solution. I hope you got that idea. It is going around the neck, but I have explained for you to understand. Right now here the same 50 ml, 50 that is 50 mole, no? So 50 mole millimole into 10 to the power of minus 3 into 100 ml by, in that 10 ml we have taken, right? 100 ml. This is volume and volume of solution in liter, no, like that it is 100 ml. In the 10 ml we have taken. So how much you will be getting? You'll be getting around 0.5 millimole. Right, now we have to identify the difference. What is the difference? Millimoles of I minus with the react copper carbonate. Millimoles of I minus which react with CuCO3. Right, now here what it is, how much you'll be getting? What is the first answer you got it? Potassium iodide 2 millimole. And unreacted part, how much you got it? Unreacted part in that 100 ml, how much you got it? 0.5 millimole. So that means millimoles of iodine which react with the copper carbonate, that only we required, right? So that means 2 minus 0.5. So that is millimole only, right? So you will get 1.5 millimole. Right, okay, now in that one more equation already I have added, right, in that picture only, right? So here copper carbonate combined with iodine, so you will get copper iodide precipitate and iodine, it is liberated. Right, now in this millimoles of copper Cu2 plus, I just write the equation for you to understand. Now the first part it is over. Now the second part it is Cu2 plus I minus, you will get Cui plus I3 minus for the second, after finishing this. So balancing according to that, here 2 and here 5 already I just made it for me. So for you, I just explained. Right now here, so millimoles of cuprous. So millimoles of Cu2 plus. According to the equation, it is 2 moles of Cu2 plus and 5 moles of I minus. You're getting 2 moles of Cui and I3 minus. So that means here millimoles of Cu2 plus. Here we go in that way. 2 by 5. 2 by 5, how do we get it? That is balanced equation according to that. Into millimoles of moles of reacted iodine. Reacted iodine which is reacted with copper carbonate, right? So that is what we are just checking, right? So millimoles of I minus which is react with copper carbonate, that only we are checking, right, from the whole, and then we are reducing that which is reacted part. So according to this balanced equation, according to stoichiometric coefficient reaction, so here 2 by 5 into 1.5, so that you will get the required millimoles. So you will get what it is, 0.6 millimoles you are getting. I hope you got that idea. Now from this we can identify the mass of copper carbonate, how much it has taken that mass for the reaction. So mass of copper carbonate, actually given mass it is different, 0.1 gram, that is different, but here unreacted part we just removed, right? So that is what, so here 0.6 mole, that is millimole, no, so into 10 to the power of minus 3 into molar mass. I just mentioned millimoles, generally given mass equal to moles into molar mass, that you know, right? Millimoles into molar mass. So here actually what it is, molar mass of copper carbonate, in the question only they mentioned 128 gram per mole, right? Okay, so when you calculate these two, why I just mentioned, no, so generally this is helping us to apply the values. That is what I just mentioned. Right now here, when you calculate this, you will get 0.074 gram, 741 here actually. 741 gram you're getting. So that is a mass of copper carbonate which is taken for the reaction. Unreacted part also it is available, but here reaction. Why I just mentioned, see again, I just bring that mind map for you to understand. See here, here 50 ml of H2SO4 and 50 ml of 0.4 m potassium iodide. In that 10 ml, now you see in this point, 10 ml has taken for that treatment to eradicate I3 minus. That is the point. So that means here 90 ml it is unreacted. So 10 ml only reacted. That is what we brought that 0.6 mole, millimole of that. Right now in that we got the mass of copper carbonate. Now we have to go with that what it is, mass percentage of copper carbonate. I hope you got that idea. Mass percentage of copper carbonate. Now this is mass of copper carbonate which is reacted of copper carbonate. Okay, now so mass percentage of copper carbonate, here what it is, mass of copper carbonate, that is what it is, reacted part of mass of copper carbonate divided by sample into 100. I hope you got how to deal this. So 0.0741 into 100, I just put it here only, divided by 0.10 gram, here also this also gram, into 100. Right now what is the answer you will be getting? You will be getting 74.1 percentage. So mass percentage of copper carbonate. So I just write it here, mass percentage of copper carbonate, it is 74.1 percentage. I hope you got the clarity about this question, right? Yes. Come on, let us check the answer here. And this mind map, I hope this will help you to identify this question, because this question looks like one paragraph, right? So option B is the correct option, right? See, generally this kind of questions and all, if you go through along, like you just to take a mind map so that it will be easy. Generally, even when we are going to some other place very deep road, so through Google Map we are reaching the place very easily, right? That too what it is, without traffic also we are going in on the spot, right? The same way here also, just you whatever you're reading according to your understanding level, you just to do the mind map, that will help you. And even some other values or different points or every data is different also. According to this, mind map will help you to reach their destination. Right now, this again, I wanted to give another method in the book method. See the same 50 into millimoles of everything, millimoles only, right? Millimoles of potassium iodide, milli equivalent of sodium thiosulfate, whatever I just mentioned very clearly here also. But my explanation, it is a little bit lengthier. For you to understand from basic to advanced, that is what I have taken a longer time for you to understand. That is the reason. I hope you just to go through this. This also, it will be easy only. Same idea only I too brought it. But only thing, it is for you to understand, it has taken longer time. And even my videos, I just increased the speed of what it is lengthier video. Due to that lengthier video, I just put that video speed so that 0.5 or 0.2 I have increased the speed of that video, so that because when that video, it is 1 hour or 1.5 hour, you'll fed up with it, or you 1 hour, how long it has taken time for that one question. But if you go through once, no, you will understand thoroughly, and whichever sum like this, if you are getting also, you are able to identify, and you will get the confidence at this only, no, it is easy like that. Yes, come on, let's go for the next question. And thank you for your great support. Next question. 1 mole of equimolar mixture of ferric oxalate and ferrous oxalate requires X mole of KMnO4 in acidic medium for complete oxidation. X is what? X means how many moles of KMnO4 we have to identify. Right now, here equimolar mixture of 1 mole, they mentioned ferric oxalate and ferrous oxalate. So that equimolar means both are half-half. So 1 mole in that half-half means 0.5, 0.5. So 1 mole of equimolar mixture, MIXTURA, mixture of ferric oxalate and ferrous oxalate. Okay, ferric oxalate. So ferric oxalate, what is the formula? Fe2C2O4 thrice. So this is actually how much mole? 0.5 mole, right? And the same way, ferrous oxalate, what it is? Ferrous oxalate, FeC2O4, that is 0.5 mole. I hope you got that idea. 1 mole in that equimolar mixture of ferric oxalate and ferrous oxalate, that is 0.5 mole. I hope you got the first point. And N factor we have to identify. Why? Because here they are mentioning about that X mole of KMnO4 in acidic medium to complete oxidation. So we have to go for N factors of oxidation. So N factors. So N factor, you know very well, N factor, to find out what it is. Number of electrons lost or gained. So number of electrons lost or gained. Right. So a number of electrons lost or gains, that is N factor, that already in many videos I explained. Okay. So now let us check with that N factor. So first one, ferric, right? Fe2C2O4 thrice. Ferric means thrice, right? Plus MnO4. MnO4, you know very well. Many times we observed permanganate ion. What is the oxidation state? It is a +5 oxidation state when it is reaches right here. So in the acidic medium only, now acidic medium H plus ion, so you will get ferrous only, of course, Fe2 plus. Right now here oxidation state, when we go for this permanganate, it is N factor, it is +5 oxidation state. Whereas ferric, actually here 2 ion is there, no? So actually it is actually what it is, N equal to 6. Ferrous, it is ferric, it is +3 only, but 2 atoms are available. So 2 atoms means per atom it is +3. So 2 atoms, each atom +3. So N equal to +6 oxidation state. And the same way, this is ferric. I just mentioned ferric. Now ferrous, let us go for it. So ferrous, what it is? Formula FeC2O4 plus MnO4 minus plus H plus ion. So here also you will get what it is, ferrous, which is converted to ferric, Fe3 plus, right? So in this, here also see CO2 plus H2O, it's common. H2O, I didn't mention here also the same, CO2 plus H2O, right? Only thing we required this one, you know. So here also I just bring that point. So here also what it is, N factor, it is +5, it's a mandatory. But here what it is, here N factor, it is +3 only oxidation C2O4 minus, that means 2 minus. So naturally you will get +3 oxidation state only. So now total equivalence of these two, Okay, so total equivalence of um, mixture. What is it? Mixture ferrous and ferric oxalate. Ferrous, ferric only we just mentioned first. Ferric and ferrous oxalate. Battery has gone down. Okay, let me check it once again. That is equal to, that is what it is, ferric and ferrous oxalate, right? Fe2C2O4 thrice plus FeC2O4. So these both together, that will be equal to equivalent of KMnO4. Okay, so that is what both we have checked, right? So this equivalent of KMnO4. So equivalent of KMnO4 equal to equivalent of KMnO4. Okay, now this is actually, as I mentioned earlier, this is 0.5 ml and this is also 0.5 ml. What is this? Here actually ferric oxalate 0.5 ml, ferrous oxalate 0.5 ml combined together 1 mole. Okay, now both complete oxidation. Now we have to find out the X, right? So complete oxidation of X, that is equal to, here what it is, first one ferric, right? 0.5 into, that is mole into n factor 6 plus, here what it is, 0.5 ferrous oxalate into 3 n factor, it is 3 ferrous oxalate, both that will be equal to X into 5, right? Okay, now this is how much you are gaining, 3 plus here this how much you are gaining, 1.5. So combined together X into 5. Okay, now X into 5, that means 5X is equal to 4.5. Right, you got it right. Now X equal to 4.5 divided by 5. So you will get how much? 0.9. So 0.9 is actually what it is, moles of what it is? KMnO4. Okay, I just write a complete point for you. 1 mole of equimolar mixture of ferric and ferrous oxalate, 1 mole of ferric and ferrous oxalate, ferrous oxalate, that is what combined together, ferric and family of ferric and ferrous oxalate and requires, how much of moles it requires? Requires how much moles? Just now we found, no, this is actually how much? Requires 0.9 moles of KMnO4, right? I hope you got that idea. Yes, come on, let us check the answer. Here, the answer it is 0.9 mole. Yeah, 0.9 mole answer is available here. Option B is the correct option. I hope you got the clarity, that is KMnO4 required in acidic medium for complete oxidation excitus. That is actually what it is. 0.9. Okay, now here everybody will ask that question, how do we get 5x? Here in this, here 5, right? Oxidation, complete oxidation of permanganate, how many electrons it is providing? So plus 5 oxidation, so that X, complete oxidation of X, so 5x, that is what we got it. I hope you got that clarity. I think I have given a better idea for you to understand. Otherwise, you just pass this video and once again you watch, so that you will come to know the clear idea. Okay, one more method in the book, what they have provided, the same thing what I mentioned, it is ferric oxalate, ferrous oxalate, how much n factor it receives. So this is the way, the same thing here, the same idea they too have provided. I think you got an X into 5, they mention, oh X, it is nothing. X we are mentioning, it is equivalence of KMnO4 here. N factor, it is what it is? 5, right? N factor, it is 5 for both. Common it is, right? So ferrous oxalate, when we are going for permanganate ion, that is also 5. Ferric, that is also 5. So you will get that X, it is 9 mole. I hope you got the complete idea.